coverage of two types of materials. One thing is going to be hitting on a final topic related to first-order delays, these building blocks that we've been talking about. And the second major topic is going to be discussing a theme that's going to stay with us for the balance of the semester. And that is nonlinearity. Nonlinearity in external systems, nonlinearity in models. And we're going to be spending some time in the implications of that nonlinearity, trying to give some sense of what it means in concrete terms, because the word is used in many different ways. And we're going to start working on building some nonlinear models. Okay. So first thing I want to do is to pose you a question. It's a model formulation question. I'd like to build up a little model using first-order delays. I'll give you a hint of sort of some natural building blocks, which would involve two coupled sets of variables or factors. One involving sort of some level of risk, and then a level of perceived risk on the part of a person. This might be risk in terms of how much effort you're putting into a class. It might be risk associated with some factor related to an infectious disease, mixing, how much care you put into washing your hands, before eating, for example. You make that extra effort in that restaurant to go use the washroom before picking up that appetizer. It may be risk associated with a chronic disease, something like, how much effort you put into working out. So there's going to be some perceived risk, and then there's going to be some actual risk. And it's going to take a bit of time for the actual risk to affect our perception of it. It takes some time to kind of appreciate a new reality. And conversely, it's going to take some time if we try to take action based on our perception to change things in the world so that the risk is lowered. The idea here is if you don't see much risk, the risk may go up, and if you see some risk, you take action to lower it. So how might we model that using first-order delays? Anyone want to proffer a suggestion? There is a model up here, but it's not directly the model we're interested in. But it's related. Anyone, though? So we're going to have perceived and experienced risk. Experienced risk is some underlying risk, not necessarily always perceived correctly. So how might we capture that?
Maybe you give the agent a choice.
Okay. So there may be an element of choice here, and the choice is based on perception, based on this perceived underlying quantity. This is a very important factor. A lot of the times in our models, remember, we're describing models that characterize, in some sense, how the world works, depict how the world might plausibly work. These models help us think through what consequences of our assumptions. And they're depicting things how they might be out in the world, some of which are known with confidence, and some of which are not, some of which are hard to observe. So we often separate what's out there from what's perceived. And it takes time to adjust that. It takes time for governments to adjust their perception of whether a social program is working, whether a policy is working, for example. And it takes time, if they've made a perception, they've had a choice to change that policy, they lower the risk by taking corrective action. It takes a time for that to happen. So there will be a choice based on perception that will lower the risk. What other elements, though? Can anyone remind me, what were the two basic forms of first-order delays? The two basic ways of phrasing them or depicting them that were mathematically identical, but we talked about them last time. Tell me what to draw for one of them in this canvas. Okay, there was an inflow and there was an outflow. Good. So we had an inflow and outflow, and maybe for the sake of those watching this from across the world in future months and years, I'll just draw it out on here. So we're going to go, hey, why am I not dragging that on here? Okay, okay, what's going on? There, hey, hello. Sorry, I'm not getting it to respond as I expected. Come on. What is going on? Okay, can we drag that on? No. Wonderful. Okay. Well, I hope posterity isn't looking at this. So let's close this guy and let's try this guy we opened last time. Let's see if it's model specific. It's model specific. The plot thickens. Okay, let's try it now. The dream of centuries. Enough said. Okay, so we might drag something on here, and one thing might be risk, and there might be an increase in risk, right? Increase in risk and decrease in risk, right? Just trying to think through the issues. This is one form that we might base a first order delay in, right? So decrease in risk or something like that. I'm sorry?
Do we have to do that?
No, you don't have to follow this. I'm just trying to think this through in a way that'll be visible for those watching the video. And if we want it to be a first order delay, what's missing? Who could tell me? What's missing here for a first order delay? Yeah, there's a key link here, and then there's some parameter associated with a parameter that adjusts, for example, how quickly, the time constant over which this adjusts, right? Do you remember that? And the decrease in risk here, to be a first order delay, what would be the formula for the decrease in risk here? Eminently examinable question. What's the formula for the decrease in risk here? For this to be a first order delay, which... Okay, well, let's make the parameter, so this is an example of bad naming. Parameters is like almost the worst name you could choose in the world for that. So what I'm going to call it instead is, it's going to be called, say something like mean time till risk change or something like that. Time to adjust risk, something like that. So suppose this is a mean time to adjust risk. What's the formula here? If you get solid about this, tough quiz is coming. Yeah, risk divided by mean time to adjust risk. If instead this was phrased as a per day chance of a risk departing, it would be times that, right? Okay. Need to be solid on this. Need to be solid on it, because we're building things on this, starting today, including this very first model. We're going to build them out of pieces. Okay, so that's one form of a first order delay. Is it not? It is. Okay, so what's the other form of first order delay? Yeah, so we have, how many stocks? One stock, and then we have what? One flow. Good. It's a net flow, right? And so you could call it like change in risk or something like that. And what would dictate that? What would dictate that? What would dictate that flow? It's based on a target. Good. Oh man, you folks are gonna, if you remember this, you're gonna keep on, do well in that final exam. Okay, so there's gonna be some feedback here, right? Is there not? I just drew this. Is there feedback? You bet there is. Because if target equals risk 2, what's this flow gonna be? 0. If target is greater than this stock, the flow is going to be positive. It's going to grow this stock, right? Okay, so those are our forms of flows, of first order delays. It's basically the forms of them. I want you to recognize this. Oh, yeah, and the formula for this guy, for the change in risk, is going to be based on some time constant as well, right? I call this a time constant, a mean time. If it's really, really long, it's going to take a long time for this top one to adjust. If it's really, really short, it will adjust very quickly. Same thing down here. It's going to be a time constant, right? Some sort of risk to time constant. Okay, to time constant. And it will basically, and that's a bad name too. I'm going to call it, it's not terrible, but it's not like parameter, but risk to, so mean time to adjust risk to. Something like that. Mean time, time to adjust risk to. Now we're gonna build on this in a bit. And then the change in risk is going to be what? It's going to be, well, okay, what's in the numerator for the change in risk? Target minus risk 2. And what's in the denominator? Mean time. It's going to be, the mean time is really, really big. If it takes a super long time, this flow is going to be, if target is greater than risk 2, the flow is going to be it's going to grow risk 2, but slowly. If this is a really short time constant, it'll change it really quick because target minus risk 2 divided by this is going to be very large, so it'll flow in very quickly. That makes sense intuitively to people? Got to kind of grok it, okay? Okay, great. So now, having seen this, having rehearsed it, now we're going to use it, okay? So we're going to change these names. I didn't ask you to follow along because we're going to be changing some things along. You might just want to build it up from scratch. But we're going to change this top one. We're going to actually have two of these bottom ones, okay? So this top one was kind of nice, but I'm going to sacrifice it. Oops. Come on. Control X. Okay. That's great. And then I'm going to take this and I'm going to copy this. Boom. And we're going to, hey, come on. Don't get over there. Okay. There we go. Boom. Okay. That's what I'm doing first. Now, we're going to build a model up out of these pieces. I told you these things are pieces. You heard a lecture about how you can string those other types I just deleted together in an aging chain. So you could have the youngest age category, the next youngest, yeah, et cetera, and getting progressively older age categories and so on. This is another model built out of these structures. In this case, it's this. And what we're going to have at the top, ladies and gentlemen, is just experienced risk. This is going to be the sort of the actual underlying risk to which people are subject. And I'm going to bring this around so it doesn't get in the way of things. And I am going to make this mean time to adjust experienced risk. Okay, the actual risk that's out there. I'm at some risk. If I go share needles with someone, I'm at a certain risk of getting Hep C or getting HIV. But my perception of it may be at variance, at odds with the actual experience risk. For some conditions like HIV, this is a very notable gap which has occurred at certain times, unfortunately, in the history where there's been a low perceived risk and it's actually been much higher, for example, early on in the epidemic, the terrible epidemic. Same thing with STIs. For example, I understand from one of our colleagues from health background that there's probably low perceived risk of STIs in long-term care facilities, in nursing homes, but there's a substantial actual risk of them. So here's a case of a difference between perception and actuality. So this is going to be actual risk, and this is going to be change in experience risk. Okay, great. Change in experienced risk. Experienced risk, great. Okay, change in experience risk. And this target here, we're going to come down to in just a second. But first, ladies and gentlemen, I want to impose an experienced risk of, and I'm not going to be picky about the units, it's going to be an initial experience risk of 1. Remember, for stocks, you have to specify an initial value. After that, their values are dictated by the flows. Thank you. Okay, good. So the initial value of this guy is going to be 1, experience risk. We're going to start with some kind of unit level of risk that's actually out there. The mean time to adjust experience risk, we're going to make it 5 time units, okay? 5 here as the default value. That'll be the value unless we override it, like in the experiment. It'll be a 5, okay? It's a double precision value, 5.0. Change in experience risk, I'd like you to, so again, 1 for the initial value of experience risk, 5 for this mean time to adjust. And ladies and gentlemen, what am I going to put into this inflow? Riddle me that. What am I going to put here? What's the formula? Good. Okay. Yeah, it's going to be target 1 minus what? Experience risk over mean time. Okay, excellent. Excellent. Now, this target 1, I'll just, for didactic reasons, I'm going to leave it with that name for now. So we want here target 1 minus the experienced risk. Hey, come on. Come on. There we are. Hey, come on. Control space. Control space will fill things in for you. I think I've mentioned that before, but control space. This is a feature of Eclipse, the framework in which this is built. You do control space after typing it, and it'll fill in the rest. Okay? And then divided by what? The mean time. Remember, any logic will not be happy unless you have the links made up here. If you don't have the link connected to it, it won't allow you. It'll complain after you try to build the model. Okay, good. So let's specify that. Okay? Now, ladies and gentlemen, we're going to go down to the bottom one. And then we're going to hitch them up together. We're going to hitch them up together. So, tell me, the bottom one is going to focus, it's just going to be the same basic thing, but in terms of perceived risk instead of experienced risk. So, I'm going to call this perceived risk. Perceived risk, okay? And I like to name the stocks with a capital, the flows with lowercase, but that's just kind of my preference. And I'm going to leave its initial value as 0, okay? As 0. It's going to be a variance between the perception and the actual. Ladies and gentlemen, the mean time to adjust risk 2, I'm going to call mean time to adjust perceived risk. Okay? Adjust perceived risk. Perceived risk. Like that. And its value is going to be 10. Okay? So it's going to take a while for our perception to reflect the actual situation. Okay? Okay? So if there's going to be a gap between target and our perceived risk, it's going to take a while for that to kind of sink in enough to change our perception of it. Okay? The value of perceiver is 0 initially. Initially 0. Okay? And this, can anyone fill in the blank for me? Change in risk is going to be called now what? Change in perceived risk, right? Okay. This would be the sort of thing that I ask you to reproduce in an exam for those who are subject to it. Okay? Good. And could anyone instruct me with the formula to fill in for that flow, for the change in perceived risk? Can anyone advance the formula? Yeah. Target minus perceived risk. I'm sorry, this is occluded in a most unseemly fashion, so let me drag this out. There we go. Here we have target minus perceived risk divided by mean time. That tells us how quickly this is going to change in response. If it changes quickly, perceived risk will quickly follow target. Otherwise, it won't. Okay. So is everyone comfortable with that? We've just done two first-order delays that are decoupled right now. And they don't exhibit very interesting dynamics now. They'll follow to what target value. The trick will be in the target. So can anyone advance for me? What will the target be of perceived risk? Oh, I should really have done this. These shouldn't have been parameters. They should have been dynamic variables. I should have planned that better. Okay. We will actually end up replacing. The easier way to do is to replace these. Okay. So, ladies and gentlemen, what is going to eventually adjust perceived risk? Perceived risk will be based on a delayed version of what? The experienced risk. So I'm actually undergoing some risk, and after some period of time, the idea here is it will sink in. It will make a difference. I'll hear about my friends who have gotten sick, or I'll learn through experience that it's really risky in one way or the other. So ladies and gentlemen, where it says target now in this formula, we're going to instead substitute experienced risk. So now the target of perceived risk, the thing that it follows, is experienced risk. It's going to be following just with some delay. If experienced risk goes way up for some reason, some change in the environment, some change in the people next to us, it'll sink in eventually. Our friends start smoking. Initially, we don't perceive so much risk associated with smoking. Maybe we start, but eventually some of our friends start to get ill from it, start to catch, develop emphysema, and maybe even seem more subject to colds and so on, and realize, wow, there's some risk associated with it. So instead of target, what we would have referred to as target, we're going to be referring to as experienced risk. I could have done it with a dynamic variable and had that in the way just to make it very clear, but I'm going to directly link these two. So we're going to take this and we're going to put it up to experienced risk. And now the formula for this guy, just as a sanity check, is going to be what? Instead of target, I'm going to put in experienced risk. So eventually the experienced risk will sink in. Eventually it will strike me, oh, this is risky. Because there'll be some number of cases where, risks plan out. Okay? And now, ladies and gentlemen, what do you think the target for this guy, for perceived risk, how is it going to depend on perceived risk? If perceived risk is higher, do you think the target will be higher or lower? Well, the idea is that if I perceive risk, I'll lower the target. I'll have a lower, I'll be more careful. I'll be less risky in my behavior. Okay, so the idea here is that the higher the perceived risk, the more careful I will be. Okay, the less likely I'll be to cause risk. I'll lower my risk. Okay, so we're going to form a link here between perceived risk and the target, which defines that mapping. Okay, and the way we're going to do it, and I should have thought ahead to this, we're going to replace target 1 by a dynamic variable here, which is going to be which we'll call the experience. Okay, so it's hitched up. This is a dynamic variable. And this will be called sort of intended risk. So it's going to be, or actually the common name for it used in modeling, we might as well call it is indicated risk. So it's kind of the risk that we're going to be trying to change based on our perceived risk. We're going to be trying to quit smoking, for example, but we might not yet succeed. We're going to be trying to exercise better hygiene, but we have to sort of learn how to do that more effectively. And so it's going to take some time to actually change the experience risk. It's going to be called indicated risk, okay? And we're going to hitch up a link from perceived risk to indicated risk here, okay? So now we've got a coupled system, and we've got to make this a negative link. We've got to make it negative polarity. So the higher perceived risk, the lower the indicated risk. Okay? So in other words, the higher the perceived risk, the lower the risk we're willing to tolerate. And there's a number of ways that we could put this in place. One way is to say this. We will put in a parameter that's called tolerated risk. Okay? Tolerated risk. And this tolerated risk will be now used to determine the indicated risk. So the tolerated risk here will be, we're going to have a sort of level of risk that we're willing to tolerate, and we'll take the difference between the tolerated risk and the perceived risk, and that will indicate some excess risk. If our perceived risk is above our tolerated risk, then we're going to try to lower our I just realized I made a mistake in wiring this, but what I'm saying is true. If our tolerated risk is above if our perceived risk is above our tolerated risk, we'll try to lower our risk, and if our perceived risk is below our tolerated risk, we won't exercise that control. So what we actually need to do here is we need to have instead of wiring this up to indicated risk, and please excuse the error, we're going to wire it up to change in experience risk, and perceived risk will also be wired up to there. So now we're going to have a gap. Let's keep it this way, but let's rename this variable. Excuse me. I'm just thinking the best way to do it, the clearest way. Let's do it actually with this variable, and let's call it excess risk. Okay? Instead of indicated risk, it will be called excess risk. Here, excess risk. Okay? Sorry about that. This is excess risk. So that's kind of the risk that is above our tolerated level. Okay? And we're going to use that to feed into this change in experience risk. Okay? And there's going to be one more change. We're going to delete that link. So we're modifying this top one a little bit to reflect the coupling with the bottom. So we will delete this one, and instead we'll have this excess risk, and here we'll just put excess risk minus the excess risk divided by mean time. So if we have excess risk beyond our tolerance, this will be flowing in negative. If we have a deficit of risk, if our perceived risk is below our tolerated risk, then we'll have a positive flow in, and therefore experience risk will be going up. So apologies about the confusions there. So what have I done? I've defined excess risk to be perceived risk minus tolerated risk. That's sort of how much we are in excess of what we'll tolerate. And then for change in experience risk, I've made it minus the excess risk, minus the difference between these two, divided by the mean time to adjust this risk. So this is kind of a reflection of the fact that we're taking action, taking a choice to lower the risk if we have excess risk, or increasing the risk if we think we're not at particular risk. So it's minus excess risk here. And that completes this little model. Okay, any questions about this? I know it's gone pretty fast, and I apologize for having to change some things. Do people understand the basic conceptual model here? So you have some underlying risk that you're actually undergoing that you don't observe directly. You have some perception of it, and that perception changes with the underlying risk, just with a delay. It takes some time for it to sink in. It takes some time for you to experience the problems which you're going to be encountering. Based on your perceived risk, you're going to have an excess risk above what you've tolerated. And if that excess risk is positive, you're going to be lowering your experience risk. You're going to be taking actions to lower it, according to some time constant. If that excess risk is negative, then, in other words, if you're below your tolerable level of risk, you're going to experience more risk. So what do you think the behavior of this will be? This is a key point. This is a key point at the nexus of, on the one hand, stock and flow models, and on the other, causal loop diagrams. What is the behavior of this model? Well, let's rehearse several behaviors we've seen. So, ladies and gentlemen, if you have a model, if you have a causal loop that is a negative loop, we saw this a lot last time, where we have a variable linked to another variable, maybe it's hunger, and maybe it's hunger and food ingested in a negative loop. It's homeostatic, it's regulatory, it adjusts for itself. What's the behavior associated with this? We saw it last time. What was that negative loop leading to over time? Equilibrium. So we could perturb it, and what would happen when we perturbed it? When we adjusted it, when we knocked it out of balance? Remember, we halved the value of the stock, and what happened? It went back. It recovered its value. Remember that? So we could knock it out of balance, it will come up to a value. We could knock it out, it will come up again. Remember that thing? We could double it, it would knock it up. It'll keep on coming back. It exhibits this kind of resilience. If you're too hungry, you go eat, and you feel full. If you are feeling overly full, you don't eat for a while, so you'll come back to a kind of normal state. Same thing with thirst, same thing with salt balance, all these different types of areas. Same thing with cold and warmth. You'll put on a jacket if you're too cold. Thermostats act in this way, right? You open the door to the house in January, and it cools off, and what happens? Thermostat discovers it discovers this imbalance, turns on the furnace, and it warms up. This is a regulatory process, very common. So here, ladies and gentlemen, we have stability. We have recovery to some mean, either from below or above. That's what we saw with first-order delays. A flow coming in, flow going up, right? First-order delays are like the simplest form of this. Okay. Ladies and gentlemen, what do we see with a positive feedback loop? Suppose you have, think about this, suppose you have a population and you have births in the population with some birth rate. So here's the population and you have some birth rate. What will happen as a result? It'll be increase. And what sort of increase will it be? Exponential increase. The population will grow. We'll go from 2 rabbits to 4 to 8 to 16. I've talked about this before. Remember that? Okay. So that's a positive loop. It's a positive loop. Part of the loop is in this length. Okay. Now, for this sort of model, what do we have in terms of loops? What do we have in terms of loops here? Well, we have two negative loops within perception. Then there's a coupling between them here, right? And fundamentally, we could draw it out, but we've got, the main thing I want to draw attention to is there's a negative loop with a delay associated with it. So it's like this, but there's a delay. If our experience risk is out of whack, what's going to happen? Is it going to make the experience risk, if it's way above our tolerable risk, what's going to happen in this system? No Greek chorus. What's going to happen if our experience risk is well above it? Well, maybe you find it hard to reason about this. So let us simulate, ladies and gentlemen. Let us compute, and let us see what happens, and then we can reason about it, okay? So ladies and gentlemen, can you run this thing? First of all, build up here. Okay, it says build completed successfully. I use this little build button, build model, and it says build completed successfully, okay? Notice there's sometimes this sort of error that it leaves there incorrectly, but it did build successfully. So let's go run this thing. Oh no, it looks like there is actually still a problem. Let's go see what it is. Let's go to the properties window, or the problems window. We're going to go to view problems. It says perceived risk is not used but is expected. So, this excess risk, I forgot to fill in a value for it. Excuse me. What's the formula for this? Perceived risk minus tolerated risk. That's what the formula is. Okay. Now it's a happy camper. Okay. Tolerated risk, thank you. It needs a value. Tolerated risk will be 0.5. Thank you. The initial value for experience risk is 1. And the initial value for perceived risk is 0. And the tolerated risk is 0.5. Okay? So what's going to happen when I run this model? Anyone want to surmise? Anyone want to guess? And if experience risk is very high compared to tolerated risk, what's going to happen? Well, it's going to lead to a change in perceived risk. That's what? If it's well above perceived risk as well, perceived risk will go up. There will be a gap between tolerated, if the experience risk is well above tolerated risk, the perceived risk will go up until the point where perceived risk equals tolerated risk. And in the meantime, it's going to be lowering experienced risk and sort of be counteracting it. But let's go up and run this thing, okay? So here we go. And let's go see what these things are doing. So here we have a model of this, and what do we see happening? We could speed this up. What do you see occurring? Okay, it's scaling. It's kind of annoying, isn't it? So let's go put in a graph. Let's not just deal with these built-in graphs. Let's go put in a graph. How do we put in a graph? Who could tell me? We've done it before. Ladies and gentlemen? How do we go put a graph into this? We did it in one of the first classes. Go down to the analysis area, drag in time plot, drag it here, and connect it up by adding a data item. And let's plot out experienced risk And then let's plot out what? Perceived risk. Okay? People comfortable with that? So I did add data item to get this, and I just filled that in. No? Is that okay? Sorry? Oh, let's do it again. So I did add data item. So I dragged in this thing from analysis, time plot, and then while this is selected, I went up here, and here, I can delete these, and then you could see it from the scratch. So here's time plot, and I just did add data item, and I typed in experienced risk, and then I did add data item again, and I did perceived risk. There you go. People okay with that? People following that? Okay, maybe I could see your errors. What are the errors? Okay, where is it? Okay, okay, call up, so if you have a problem, call up this problems window, and then make it so I can see it. There's a description down there. Okay, that's exciting. Okay, so that's mean time to adjust experience risk. Mean time to adjust experience risk. Oh wow, that's really interesting. Misplaced constants. Okay. If I were you, I would delete. Okay, here it is. Experience risk. Okay. I
have target one.
Yeah, you may have target. Maybe, yeah, but yeah. Okay, so folks, what do we see as a result? You can run it while I was looking at that, but what do we see as a result? What do we see in terms of behavior here? We could, of course, speed this up, but okay. Okay. So let's reason about this. The basic deal here, this is like a highly examinable point. When you have a negative feedback with very little delay or almost no delay, what you get is this great stability. If you have a negative feedback with a delay, what you get is oscillations. It will go up, but it will tend to overshoot its target. So it will rise, but it will overshoot, and then it will start going down again to correct, but it will overshoot and then go up and then down. It's a little bit like driving on ice, where you tend to overcompensate and go too much to the left and then adjust and you go to the right. So if you have a negative feedback with a delay, you get oscillations out. And we see these oscillations here. Ladies and gentlemen, this may seem an odd artifact of this particular model. This model is just one of thousands that will illustrate this behavior, but it's a particularly simple one. It's a particularly simple one. Ladies and gentlemen, perceived risk here is a delayed version of experienced risk. And what we have up here is a standard first-order delay, but with a twist. Instead of being a classic first-order delay where you'd have a target minus experienced risk divided by the thing, you have target minus a delayed version of experienced risk, namely perceived risk. And that leads to those oscillations. It overshoots. If you just had target minus experience risk, you get this sort of behavior of a classic first-order delay. We saw that last time. When you have target minus, when you have this target, tolerated risk, minus a delayed version of experience risk, which is what perceived risk is. That's when you get oscillations. It's adjusting for the target, but it's adjusting with this delay. And so it goes too far. And then it compensates and goes too far that way. But eventually it's reaching a sort of equilibrium. By the way, why do I say perceived risk? I could see a very nice exam question. Very nice exam question. Even a pop quiz question. Why do I say perceived risk is a delayed version of experience risk? Because the bottom construct here is what? It's a what? First order delay. It's a first order delay of which target? Of experience risk. Experience risk is serving as the target here. Do you folks recognize this from last time? This is the same thing we had last time, except instead of a variable called target, we have just experience risk substituted in. Do you remember that? Okay. So instead of having target minus perceived risk as the basis for the flow, it's experience risk. So experience risk is serving as the target for perceived risk. Perceived risk is a delayed version of target. It's a first order delay here in terms of the value of the stock. Remember I told you at the end of lecture last time that with a target formulation of this, you can get the stock value being a delayed version of the target. Remember that? It's the value of the stock. So perceived risk is a delayed version of experience risk. So experience, this top one here, this top formulation here is, ladies and gentlemen, a first order delay, but it's a first order delay with a twist. And what's the twist? The twist is that it's a target, tolerated risk, minus not experienced risk, as it would normally appear in a first order delay, but minus perceived risk, it's just the delayed version of experienced risk. So here, the target is something that's a delayed the target is tolerated risk, but it's adjusting this delayed version of experienced risk. And that leads to these overshoots. So we have these oscillations come out. And it's believed that similar oscillations explain a lot of the oscillations we see in the real world. That when you have systems that exhibit negative feedbacks with long delays, you get these overshoot phenomena. You get cycles. You get oscillations out of them. Oscillations like this are experienced in many natural systems. They're experienced in many human systems. And they're a reflection of a control mechanism, of a governing loop, of a homeostatic type of thing, but with a long delay. And if your thermostat in your home were reporting not the current temperature, but the temperature as of an hour ago, you would get these sort of cycles in your home where it will become way too hot because, it will be heating it up, but it's getting a reading from an hour ago. It's heating it up to the level you want, but it's still saying it's too cold because it's getting the reading from an hour ago. So it keeps on heating it up, and it's gone way above your comfortable level. And then it realizes, oops, I'm way above the comfortable level, so it starts cooling down. And of course, it will keep on cooling down too long. So that's what's going on. Does that make sense? When you have a negative feedback with a delay, just think of this bottom one here as just being a module that gives a delayed version of experience risk. And so you have the target minus the delayed version of experienced risk divided by this time to adjust. That's what you're basing it on. It's like a delayed thermostat. You're going to get these cycles. Does that make sense to people? Okay. Now, if you go in, those of you who are mathematically inclined, if you go in and look at the differential equations, guess what will come out of this? When you have two coupled stocks, what do you have in terms of a differential equation? You have a series of differential equations, two state variables. It's equivalent to what order differential equation? Second order. It's like having dx dt and dy dt. And that's when you can start getting cycle in place. And you can analyze this from a differential equation standpoint, solve it, and you'll actually find that there's complex exponentials of this form, e to the a plus ib times t, or in engineering they'd write this often as j. This is imaginary. This is a complex number. And this leads to a damped exponential, something like e to the minus alpha t times sine of theta t times sine of theta t. And it leads to damped oscillations. And then there's a cosine term as well. In any case, there's damped oscillations that come out of it. So, ladies and gentlemen, when you have a negative feedback with a delay, you get oscillations out. That's the key take-home point there. And I want you to know these things. When we have a negative feedback, we get the stability. When we have positive feedback, we get this growth. And when we have negative feedback with a delay, we get oscillations. And the final bit of this, ladies and gentlemen, I'd like to actually, just to show that first one. We haven't done that. Let's just do it. It takes about less than 5 minutes. So, ladies and gentlemen, let's go grab that. So let's go create a stock. Let's say this one away. It's a one worthy of billing all its own. And let's create a new model. And ladies and gentlemen, this one will be a model well, I'm going to call it rabbits. Okay? We're going to call it the rabbit model. Okay? Here we go. Model A, come on. You can do Control N and call it rabbit. Rabbit. Okay. Here's rabbit. Okay. So we're going to have a positive feedback loop. Ladies and gentlemen, I'd like to drag in a population here, and so it's a stock, and I'm going to have a flow in, which are going to be let's call it net births or net change in population, and then we're going to go up and we're going to create a parameter called net population growth rate. Okay, and I could have called it birth rate, but then someone would say, well, what about deaths? And this is going to be a net population birth rate, net population growth rate. And I'm going to say that this is going to grow at 2%, say 2% per year. Okay? So net population growth rate will be 0.02. And this is going to be an initial population of 2 rabbits. And the formula for net change in population is going to be the net population growth rate times the population. Net population, population growth rate times population. Okay? So, ladies and gentlemen, can anyone give me the formula for this in terms of the state equations, in terms of the differential equations? What's the formula for this? Let's call the population X. What's on the left-hand side? X dot, the derivative of X with respect to time, the rate of change of X with respect to time, number of rabbits of increase in the population per unit time, per year, say. And this is going to equal what on the right-hand side? There's only one inflow, so there's some plus on the right-hand side. What is it going to be? Let's call net population growth rate alpha. So what's going to be on the right-hand side? Alpha X. And what's the solution to that? Well, it's some initial population times e to the alpha t. And alpha here is positive, so it's going to grow like gangbusters. It's going to grow at e to the alpha t. It's going to grow exponentially. So let's run this thing. And what do you think we're going to see? It's growing, and we can create a little graph of it. And at first it looks almost linear, but you speed it up, and it's going to be growing and growing and growing and growing. And the faster the population is, the faster the growth of the population in terms of rabbits per year. Fastest population, the more rabbits come in per year. It's going to go from 2 to 4 to 8, right? Just keeps on growing. You could see it's very large indeed, up into the tens of thousands, if not hundreds of thousands now, and it just keeps on growing exponentially without bound. That, ladies and gentlemen, is this case of a positive feedback. So positive feedbacks lead to instability. They lead to divergent behavior, exploding behavior, faster and faster and faster growth. Companies often like it. Natural systems are not so resilient to that. It can only go on so long. Sometimes it's very deleterious. Think cancers. Just divide and divide and divide. Negative feedbacks lead to stability, stasis. They seek a balance. Negative feedbacks of the delay lead to equilibria. Lead to oscillations which approach equilibria typically. Are people okay with that? Okay. Now, ladies and gentlemen, I want to go on and talk about the final little bit of this. So this is our rabbit population. Maybe I should have called it negative feedback. Yeah, question.
What's the value for population?
2. Initial value for population is 2. And the value of net population growth rate is 0.02. Okay? So that's, I could have, if I had more time with that model, I would have had births and deaths, and I could have had the birth rate be 4% and the death rate be 2%. It will be a net positive of 2% growth rate. We could have gone into that, and I would welcome you to do that. You'll be seeing more of that sort of stuff in your problem set, which is posted. Okay. So now I'd like to step back for a second. All of the models that we've been looking at, those that exhibited oscillations, exponential growth, and the stasis, they exhibit this interesting behavior, even some emergent behaviors, things we didn't expect from any one piece of it. By coupling them together, you get this interesting behavior. Like by coupling these two first-order delays of sort, you get these oscillations. Great. Nice. But, ladies and gentlemen, the models that we've been building share a characteristic here. And the characteristic is they are linear models, okay? When I talk about linearity here, I mean it in a quite particular sense. We talk about linearity of a function in mathematical terms if we have certain properties observed. Suppose we have a function that takes in, for example, a number and it spits out a number. So maybe it takes in a number x and it doubles it, for example. Or maybe it takes in a number x and it divides it by 5. We call functions like that linear. You give them a certain multiple times that number, it will spit out multiple times the function applied to that number. So if you have a function, for example, which doubles the number, you feed in 2, and it gives you out 4, for example. If you were to feed in 3 times 2, it would give out 12, right? Doubling of 6. And that's the same as looking at 3 times 4. 3 times that function applied to the original number, 2. So with a linear function, if you take the input and you double it, you're going to get out double the result that you would have gotten with that input. If you take two inputs, you consider them each independently, and you consider the response of the system to each of those. With a linear system, you're going to get something else that's simply the sum of the responses to each in isolation. Linearity is a beautiful property when it happens. We can use it to all sorts of good effect to understand a system. And it's very valuable to understand that this operates for certain types of analysis very legitimately. But for a lot of systems, we don't have this nice property in place. The world in general exhibits nonlinear properties where these features break down. If we have two policies, for example, and we're considering the response of the healthcare system to two policies that were put into place, we can't simply say, well, let's consider its result to one and the result to the other, and then combine them together to find the cost savings from both together, or the benefits of both together. It doesn't work that way. Sometimes they work at cross purposes. Sometimes they interfere with each other. Sometimes they synergize with each other. Linear systems work to a degree often, but then at some point they become nonlinear. A bridge, as we know from Galloping-Gertie, the Tacoma-Narrows bridge, for a certain regime it's linear. It'll respond in a responsive way. It'll be elastic, and at some point it rips apart. It becomes nonlinear. It enters the plastic regime in the language of mechanical engineering. So here we have a situation of linearity which is observed for certain systems over small ranges. And ladies and gentlemen, all the systems we've been looking at thus far are linear. If we had gone back and we had doubled the number of rabbits initially in that model, or we had gone back and doubled the values for that stock, so the experience risk was 2 instead of 1 initially, we would have gotten results out. If we had systematically gone through and doubled the initial values for stocks, we would have gotten out results to systematically double the values. And in general, we don't have such neat properties. For linear functions, okay, it looks like, for linear functions, I'm not sure why it's cut off here. The function behaves with respect, if we want to understand how the function behaves with respect to some input, maybe a set of policies that we want to test it against, maybe some initial condition. We simply understand how it responds to a set of pieces, and then we could sum its response to each of those pieces up to get its response to the whole thing. And we do this in engineering a lot. Those who are from engineering background will know we decompose a signal into sinusoids. We analyze the response of the system with respect to each of those sinusoids, and we sum those up to get the response to the whole thing. This is a routine method of analysis in engineering, and it works great for a linear system. And in engineering, we often work with LTI systems, linear time invariant systems, and it's great stuff. But the world in general is not linear, and it has profound consequences for this class that it's nonlinear. So with a linear system, if we have some situation, we can break it up into a bunch of pieces, x of I, analyze the response to the system, this is f of x of I over here, and just total up the response of the system to each of those pieces. It's beautiful. In a linear system, in the linear regime. And all of the systems we've been examining are linear with respect to state variables. I'm going to go on from this, but I will just note that that within the context of infectious disease modeling, we will be dealing with nonlinear systems. And nonlinear systems are the subject of rich analysis in applied mathematics. And we don't require that from all the people in this class. There's many people who do this sort of modeling who are not mathematicians, but if you have an appreciation for the underlying math, you can go very far with understanding these systems. And there's much you can do on the basis of linear algebra, calculus, differential equations, some numerical analysis, control theory, complex analysis. Any of these areas, if you know it, it fits in beautifully here. We don't have time to go into this in detail, but over the next few lectures, we're going to have a chance to look at some ways that mathematics sheds light on the behavior of these models, of nonlinear models. But in general, ladies and gentlemen, we're not going to be able to write a formula for how the model will behave. You'll see up here I wrote a formula for how the model behaves over time. This model here with the rabbits, I could write a formula for it. This model here with the stasis, the negative feedback, I could write a formula for how it will behave. Because it's linear, I can solve it. With nonlinear models, we don't have that luxury. We can't break the input up into pieces and solve how it behaves with respect to each piece, and we can't write a formula down. The only way we're going to know how it behaves is by running the model numerically and performing what's called a numerical simulation of it over time. And this is where simulation becomes not just a useful tool, but an essential tool to understand the behavior of these systems. And most systems we deal with in the world are nonlinear. Human systems, systems involving things like traffic flow, like competition between companies, like health issues in a population, the dynamics of health issues, they're terribly nonlinear. We can't pretend to approximate them in a linear way over more than a very short period of time and in a very short situation, very confined situation. So we'll be using the tools of math, of applied math, in the next two lectures to analyze some of these systems. But we will be doing it in a way that is constrained and that helps us understand the behavior of nonlinear systems. So when we're dealing with these systems, we're going to be using as an example models of contagion. Contagion is reflective of processes whereby we have some factor. Often it's an infectious disease, will be pathogen, a bug, a germ that's propagating through a population from one person to the next to the next. Sometimes it goes to surfaces, not just people to people, but people to surface, or person into the environment, and then someone else gets it. And we see it spreading through that population. But these are not the only examples of contagion, not the only examples where you see something spread from person to person to person even. What other examples of phenomena do we see, of processes do we see, where we see this sort of propagation through a population from one person to another? What sort of things pass?
I have a question.
Yeah.
Is there ever a time when a nonlinear model could be transformed into a linear?
Absolutely. And the hitch, though, of this, Mustafa, is that when you transform it into a linear model, that typically remains valid, remains safe in a sense that it's accurate for a short period of time or in a small context. So if you have, for example, you're from a health background, if you have a situation where you have an equilibrium in a disease where there's some level of some condition circulating in the population. It's not growing quickly. It's not. It doesn't exhibit big dynamics. You might do what's called linearize a model around that point, meaning you sort of confine your attention to that situation. You say, okay, in this situation, kind of let's understand what's going on. And there a linear approximation will work very well. And at a mathematical level, those of you from math background will perhaps be familiar with taking Jacobians, for example, of a nonlinear system. So we take a system that's nonlinear, like one of these system dynamics models, and we linearize it by understanding its behavior in a way that is linear at that certain point. And that's a decent approximation for what's going around there. And you can get some understanding from that. The problem is that the situation is totally different if it somehow gets nudged out of that situation. And And often what we'll do, if we want to analyze something, is we'll linearize it around successive points. So at this point, we'll kind of understand what's going on, and then we'll take a little bit of a step. Things are changed. We'll re-linearize it there, kind of understand what's going on. And we can often do that. For example, if you wanted to highlight which these stock and flow models have causal loops that can be imposed to sort of highlight which areas of the model are active right now, which areas of the models are driving behavior right now. As we'll see, as you run a model over time, a stock and flow model, which areas of the model are the dominant ones, or the main ones, or the ones most shaping the behavior will change. And you can highlight which of those loops are the dominant ones at a given point in time, but you can only do that by linearizing the model at given points. So you kind of linearize at one point, show which loops are dominant, and then you go for a little bit, linearize it there, which loops are dominant, and over time it will change. Is that helpful?
So your point is
yeah.
It's dangerous to generalize it to the whole.
Yeah, you generally can't take that linear approximation and use it for all time. It will just be ludicrously off. And unfortunately, in certain fields, that has been done for most periods of time because people didn't have computational horsepower to simulate it. So linearized models with matrices, which is linear algebra, was used as kind of the dominant form of analysis. So in economics, for example, understanding equilibrium behavior of a system around some market equilibrium is a dominant mode. And you can do that as long as you're at equilibrium. System dynamics and these sort of models are used to understand disequilibria behavior, like competition between firms where one firm is growing, Google is growing and Microsoft is struggling or something. That's an example where linear approximations can be really problematic. The market is shifting, and these sort of models help you understand that disequilibria. Is that helpful? Yeah. Any other questions? So the next several lectures, 2 lectures, we're going to be going through understanding associated with processes of contagion. I did ask a question. What other processes of contagion besides the spread of something like flu or polio or HIV, what other sorts of contagion is there? Something not related to pathogen. What other things spread? Gossip. What other things? Yawning. Yes. Standing ovations, actually. One person stands up, someone else feels inspired, stands up, more people stand up. People have done neat models of that. How about other things? Ideas, memes, types of behaviors, behavioral norms change. People, fashion spreads in this sort of way. Innovation spreads in this way. People see something novel going on here, they start imitating it. This is known even among groups of animals. Some animals are tool users, some certain types of primates, and it will spread, and innovation will spread from one group to another group by observation. These are examples, ladies and gentlemen, of contagion. And the basic that we will see over the next 2 lectures will apply to all those things as well. They'll apply to spread of word of mouth about products, about ideas spread. So while it will be focused on contagion, you'll be able to systematically map from the space of health concepts to the space associated with exposure to ideas, in terms of willingness to innovate and engagement in innovation in terms of product consumption of products, etc. So a lot of what we'll be talking about will seem very focused on health, but it will actually be highly transferable, and there's whole models that are focused on that. So that's all for today. I have posted the assignments. I also sent mail to a number of people asking about specific project ideas, and I've asked some groups to consider meeting me after class today. And I've been meeting some groups also outside in my office. And I've been trying to connect people who I think could work together fruitfully. So if you'd like to come up and talk about projects right now, you'd be welcome to do so.